Welcome to Logistic Growth. So, this is another Calculus 2 concept for differential equations. So, if it is a differential equation, or if it is a logistic growth, it will follow the form of this. So, you have your constant times p times 1 minus the population over the carrying capacity. So we have this first term here. It's like all of our others. It's just some constant that you might have to solve for. That's just our exponential growth or decay constant. And then we have this is a carrying capacity. And so what logistic growth looks like is you're going to have something where it's going to start up speeding really fast and then it's going to slow down and then it's going to stop. And so this uh, height right here, so basically goes to, this is L, your carrying capacity. And another key thing is this is like this is where the rate of change is the quickest. This is at L over 2, which is pretty cool. So, like we have done for the other ones, let's go ahead and integrate this. This is going to be our hardest to integrate, and so we're not going to ever manually integrate this after this. I'm just going to start off with the form if we know it's a logistic growth type of thing. So we know we're going to first try and separate the variables here. So you have, let's do kt or kdt is going to be dp over p times 1 over, or 1 minus p over l. And so you're going to notice that this is going to be some partial fractions. So the partial fractions state that you have something A and B so that we can have just P and 1 minus P over L here. And so we need to solve for these things A and B so that we could just integrate this with respect to P. That's the goal here, is to find these values of A and B. So what I'm going to do is I'm going to actually multiply everything by L. That'll probably be the best way to go about doing this. So we have L over P times uh, L minus P. So this is another form this could take place in, is it's in the terms of, let's see it, Kp times L minus P. But anyway, we're going to have this be in the form of A over P plus B over L minus P. So when you multiply everything by their correct, by the least common multiple, you get L is equal to uh, A times L minus P, and then BP plus BP. And so then you want to set this equal to, we want to set values for P to basically solve for A and B. And so by doing your fancy algebra stuff, you end up getting that we can rewrite such that A and B is equal to 1. So now we can go integrate 1 over P and 1 over um, L minus P dP, which is going to be equal to k dt. We're just going to write kt plus c, because we already know that that is the integral of k dt. And so now, this integral on the left-hand side is ln p, and the integral on the over here is going to be minus the natural log of L minus p, and the reason it's negative here is because there's a negative p here. So that's going to be equal to k t plus c, and then you can combine these logarithms, so that's going to be ln of p over L minus p is equal to k t plus c, and then we exponentiate, so p over L minus p is going to be equal to e to the k t plus c. Clean up the board a little bit, but I think the best way to probably solve for p here is that we're going to reciprocate everything. So we're going to do L minus p over p. I'll do this smaller. L minus p over p is going to be equal to e to the, and instead we're just going to uh, have a negative exponent because we reciprocated it, kk, kt, and then we're going to do plus c. And then with our plus c, what we could do is we can write, technically it's minus c, but we're going to just do what we did in the other videos where we just said, let's let e to the minus c be a constant a. So now that we have, so now we can just have a times r e to the negative kt, e to the negative kt. Boom. All right, so now on the left-hand side, we could say, we could break apart this fraction. And so this is just -1 based upon breaking up the fraction. And then we can add 1 to both sides. So I'll just add 1. So +1 +1. And then we are going to reciprocate and then divide by L, or I guess multiply by L at that point. So now we have P is equal to um, L over, and then we have 1 plus a, which is just a constant, e to the negative k t. Yes, this is an absolute mess, and this is why I'm going to just say memorize this for logistic growth. So whenever you have a logistic growth, remember its carrying capacity over 1 plus the constant e to the negative kt. But let's do a sample problem because that was chaotic. All right, we have our question here, and there are 3 parts to it. So we're going to write a over here. This is going to be the quickest because it is a simple differential equation. Let's just write the differential equation. A wildlife preserve can hold no more than 100 coyotes. So that means L is equal to 100. K is 0.1. Then we have K is equal to 0.1. 0.1. So now we can just substitute that into our differential form. So dp dt. And so we have kp, so that's 0.1, times p is going to be equal to 1 minus p over L, and L is 100. And A is as simple as that. Now for part B. And this is where it gets kind of weird. So we remember our form from the last time. That is the population is going to be L, which we have 1 plus A e to the negative k t. So this is the form it will take on. Just like this. But now to like actually substitute in these values. So we know that at t equals 0, the population is 20. So we have 20 is equal to the carrying capacity, which is 100, times, or over 1 plus a. We don't know what a is. And then we want e to the negative kt, but t is equal to 0, so it's just going to be e to the 0, which is 1. So now we can just solve for a. We can, let's probably reciprocate both sides. And so we're going to say 1 plus a over 100. And now we reciprocate the left-hand side. So it's 1 over 20. Multiply both sides by 100. So it's 100 over 20, or 10 over 2, is equal to 1 plus a. So 10 over 2 is 5 equals 1 plus a. And a is equal to 4. And now we can substitute it in and get our very specific solution. So P of t is now 100 over 1 plus 4 e to the negative 0.1 times t. And so that is part B. And we can do very similar work here for 80. So we know that the population won't reach above 100 because that is the horizontal asymptote. But we want to see when it's going to reach 80. So let's do basically the exact same thing we did over here. And if we hadn't memorized this form, then we would have to have manually integrated this. And I don't want to deal with any more partial fractions, so we're just going to memorize this form. And so we're going to set 80 to be 100 over 1 plus, but this time we have 4 e to the negative 0.1 times e. And we need to solve for t. So we're going to multiply both sides by the entire denominator. And then I'm going to also divide by 80. So now we have 1 plus 4 e to the negative 0.1 t is equal to 100 over 80 is 10 over 8, which is 5 by 4. And then we're going to also subtract 1 to get rid of that 1. And so now we can also divide by 4 here at the same time. So 5 by 4 minus 1 is 1/4. Just going to set this equal to 1/4. And then we're going to divide by 4 again. So we're going to say times 1/4. And so now we have e to the negative 0.1 t is equal to 1 over 16. Take the natural log of both sides to get rid of the e. So it's going to be negative 0.1 t is going to be ln of 16, 1 over 16. And then we can divide both sides by 0.1 and get that t is about 27 years. 27.7 years.